The band model can finally start to give us some sense of how materials conduct current and how much current they can conduct. So let's begin by rehashing the band model for silicon or for any other kind of semiconductor. What we observed is that as we looked at energy levels from the bottom to the top, we observed one final full energy level, the energy band, and then a forbidden gap followed by a mostly empty band. We called the full band the valence band because it is full of electrons that contribute to covalent bonds. We call the empty band the conduction band, and we call the amount of energy that separates them the forbidden gap or the energy gap or the band gap. So this is the forbidden gap or the band gap. Of course, the amount of energy in the band gap is the most important parameter that characterizes the conductivity of a certain material, whether it is a semiconductor or anything else. This is obvious because this is the amount of energy that electrons in the valence band need to gain from the system around them. Whether they gain it from thermal energy or from any other kind of energy is still to be decided, but it is the amount of energy that we have to gain before we can become conductive. So we have to measure this amount of energy in the band gap, which is given the symbol Eg. The conduction band is going to be given the contraction Cb and the valence band Vb. Now, we are measuring very small amounts of energy because we are measuring energies for electrons. So when we use joule as a measure of energy, it's going to be unwieldy. So we use another unit for measuring energy, which is called the electron volt. And 1 electron volt is equal to 1 joule multiplied by the charge of an electron, Q. And so basically it's 1.6 times 10 to the power of minus 19 joule. So that's 1 electron volt. You can think of an electron volt as a scaled version of the joule, just a contraction of the joule so that we can measure it in units that are not as unwieldy and do not contain a lot of negative exponents. But it has a physical meaning. So 1 electron volt is actually the amount of energy that is required to bring an electron from ground up to a potential of 1 volt. So that's what 1 electron volt is, because basically it is E times Q, and that's the definition of potential. So what's the band gap? How much is Eg in terms of electron volts? It's 1.1 electron volts. Actually, it's 1.12 electron volts, and it keeps going, so it's an irrational number. But it's roughly 1.1 electron volts. So how much is that in joule? It's 1.1 times 1.6 times 10 to the power of minus 19 joule. But what does it mean? Is this a lot of energy or a small amount of energy? So this is basically the amount of energy that an electron in the full valence band has to obtain somehow in order to jump into the conduction band. So where's it going to get it? So far we haven't talked about anything other than thermal energy. So thermal energy is generally kT. So this is the amount of thermal energy in the system. At room temperature, for T equals 300 Kelvin, thermal energy is going to be roughly 25 milli-electron volt. So it is 25 milli-electron volt while the band gap is 1 electron volt. So we are talking at least 2 orders of magnitude smaller. The amount of thermal energy in the system is at least 2 orders of magnitude smaller than the amount of energy we need to cross the band gap. So what does that mean? That means that it is really hard for electrons to jump from the valence band into the conduction band. Does that mean that no electron is going to make it across? No, some electrons are going to make it across because thermal energy is a random process. So not all electrons are going to get the 25 milli-electron volts. Some are going to get bigger energy, some are going to get smaller energy. But those electrons, the proportion of electrons that manage to get 1.1 electron volt or more will be very small. So we can conclude that the concentration, the number of electrons that make it across the band gap is going to be very small. That's what we can say for now. But some are going to make it across. And so if this electron makes it across, it ends up in the conduction band. And what it leaves behind in the valence band is an empty position. So there's an empty position in the valence band here. What we have to think about now is how this affects conductivity. Conductivity is a material property which measures how much the material is capable of carrying current if it is exposed to an electric field. And so if we expose this material to an electric field in this direction, the electron in the conduction band will start to move in the opposite direction. Why is the electron capable of moving? Because the conduction band is full of empty energy states. These energy states are ready to receive the electron if it starts to move, and so it can move. Now, the electrons in the valence band do not have a lot of free energy states to move into. They actually, in this situation we have drawn, have only one energy state that is empty, which is the empty location that the electron has left behind. But that allows it to move, and so this empty location is going to start to move towards the right. Recall that it's not actually the empty energy states that are moving. It's electrons in the valence band that are moving. So an electron will move here and occupy this empty state and leaves behind the state itself. Now an electron from here is going to jump here and occupy this empty state, and it's going to leave behind an empty state in its stead. So instead of following all the valence band electrons that are moving from right to left, it's easier to follow the empty location as it moves from left to right. We call this empty location a hole, and it has a charge equal to that of an electron, but it is positive because it is moving in the same direction as the electric field. And so there is an electron current formed by free electrons in the conduction band that are moving against the electric field. There's also a hole current, we call IP, that is also moving in the same direction as the electric field. So the total current is going to be IN plus IP. Now let's think about what allows current to flow. There are two things that are required for current to flow: free charges, or electrons, basically, and empty locations for these electrons to move into, meaning empty states for them to be able to move into. The valence band is very rich in electrons, but it is very poor in empty locations. The conduction band is very rich in empty locations, but it is very poor in electrons. So when an electron jumps into the conduction band, the presence of an electron in the conduction band is something to note. But when it leaves behind an empty state in the valence band, it is the empty state that is worth noting. Now, the proportion of electrons that manage to jump into the conduction band is obviously going to be a function of the temperature of the system. The more the temperature, the more electrons manage to go up. Now, when that happens, we have more electrons able to move within the material, which means that the conductivity of the material improves. So the conductivity of a semiconductor is going to be a function of temperature, and it's generally going to increase with temperature because we generally have more charge carriers in either the conduction band or the valence band. Recall that charge carriers now in the conduction band are the free electrons. Charge carriers in the valence band are the holes. Now, let's consider semiconductors and metals or conductors and compare them to semiconductors. So insulators or dielectrics as compared to semiconductors. When we look at insulators, we will observe something very similar to semiconductors. So we will observe full bands and then suddenly empty bands, right, at 0 Kelvin. But the difference between an insulator and a semiconductor is that the highest full band and the lowest empty band, basically the conduction band and the valence band of a semiconductor, are separated by a very large band gap, Eg. So the only difference between a semiconductor and an insulator so far is actually the amount of energy in Eg. We will find another difference when we talk about dopants, but so far this is the only difference. In fact, in insulators, Eg is so high that at normal operating temperatures, you can assume that no electrons make it across the band gap. And therefore, the valence band is completely full, and the conduction band is completely empty. What that means is that there are no free locations for electrons to move through in the valence band. There are no electrons to move at all in the conduction band. And therefore, when you expose an insulator to an electric field, nothing moves. The electrons in the valence band are all stable in covalent bonds. There are no empty states. Conduction band is completely empty. And so you can think of the conductivity of an insulator as equal to null, whereas the conductivity of a semiconductor is not only not equal to null, but is a function of temperature. So what is a conductor or a metal? For a conductor or a metal, what happens is you observe full energy bands as you go up, and then instead of seeing a full band followed by an empty band, what you observe is one of two things. Either a band that is only half full at 0 Kelvin, or you observe a full band and an empty band that overlap. So basically they have a negative EG, a band gap that is less than 0. In both situations, we end up with the same result, and the result is a continuous band of energy levels, which is not full. So what this band has now is a lot of electrons and a lot of empty states. Because it has a bounty of both empty states and electrons, it has a very high conductivity, and in general we will assume that the conductivity is infinite. For a semiconductor, on the other hand, the situation is neither as dire as an insulator nor as good as a metal. We have a finite positive band gap, but it is not huge, and so at operating temperatures we can see some electrons making it across the band gap. This creates some empty states in the valence band and some electrons in the conduction band. Not nearly as plentiful as the mixed band in a metal, not nearly as bad as an insulator. It is a semiconductor.